will be giving a lecture today on discrete time sliding mode control. So before he starts the lecture, although he is very well known, I will introduce him to the students and the audience that Professor Xing received BSc degree and MSc degree from University of Science and Technology of China, and in 1982 and 1984 and PhD degree from Southeast University, Nanjing, China in 1988. He is now with RMIT, University Melbourne, Australia, where he is the director of RMIT Platform Technologies Research Institute. Professor Xing research interests include variable structure and nonlinear control, complex and intelligent systems and applications. He has published over 350 refereed papers in technical journals, books, and conference proceedings. Professor Xing served or serving as an associate editor of IEEE Transactions on Circuits and Systems Part 1, IEEE Transactions on Industrial Informatics, IEEE Transactions on Industrial Electronics, and several other scholarly journals. He received in 1995 Central Queensland University Vice Chancellor Award for Research, a Jiang Scholar Award from Ministry of Education of China in 2009, and was made Emeritus Professor of Central Queensland University in 2002 for his long-term contribution. Professor Xing is an IEEE Fellow, Vice President Planning of IEEE Industrial Electronics Society, and an IEEE Distinguished Lecturer. He is also a Fellow of the Institute of Engineers, Australia. He has many contributions, many areas, and one of his very strong contributions in control theory, in sliding mode control theory, that the terminal sliding mode control. It is theoretically very sound, as well as it has a lot of practical application. He has shown the first time in sliding mode literature that in sliding mode the states of the system can go to 0 in finite time, and what is termed as terminal sliding mode control, and which has also very great practical applications. I do not want to come between lecture and you. I invite first Mrs. Korude to present him a flower bouquet, and then he will start his lecture.
Okay. Thank you very much. Firstly, it's a great pleasure to be here in Bombay, Mumbai, India. I always wanted to come to India because this is a fascinating place. As you probably know, that many of the religions actually come from India. Buddhism is one of the things widely practiced by Chinese people, and certainly this opportunity. Even so, we are not that close. So next time I will have to make sure I will be very close to that place and sitting under that big tree, to think about the meaning of life, which is we all have to do, I think, some stage of life. Firstly, I would like to really thank Professor Babemdoya inviting me, and also IIT Bombay to host my visit. Professor Babemdoya is very famous, and one of the reasons I'm coming here is really not just to make the presentation, rather we have some in-depth discussions on the sliding mode. Certainly there is some very original work done in here, so that I will do some very brief mention later on. What I'm going to talk about today is sliding mode control in discrete time. This is actually the earliest work I did. Actually, I'm more proud of this work than the terminal sliding mode, even so many people mention terminal sliding mode. So what I want to talk about today is really not necessarily giving you sort of a theoretical, the background foundations. What I really want to do is using some simple examples to demonstrate the essence of sliding mode and the key problems in the sliding mode in discrete time, and in particular some fascinating behavior I don't think many people in engineering you are aware of, because we use some mathematical theory in the chaos theory, using that to look at this kind of a very interesting behavior in discrete time. Okay, so here is some of the slides. some of slides. Okay. Here's some of the slides. You can see that that's firstly I'll give a very quick introduction of sliding mode, and then we look at sample data. What are the key issues in sampling data? And then we look at basically discrete time, sliding mode control. Basically, there's two school of thoughts, right? So what I'll give you is some description of those. And finally, I want to have some discussion, which I think is very important, is look at what are the key issues in the years to come. Okay. As I said before, I'm not going to mention very theoretical stuff. What I want to do is using very simple engineering problems, and then to try to demonstrate a key concept. I think as an engineer, I mean, the thing is, the intuition is most important. We should not be carried away by mathematics. Mathematics is only a tool. So I think understand physical meaning, I think more important than actually understanding the mathematics. So here is just some of demonstration. Look at the sliding mode. You can see that on this chart, you can see that this is everybody knows this double integrator, right? And if we know that if we have only one state feedback, we know that it is not full state. You will not be able to control the system asymptotic stable, but you can control stable. Stable, for example, if this is a real number k greater than 0, so you have this kind of a oscillator, without any damping. So it's stable, but not asymptotic stable. So, and we know that system is actually preserving the energy. So then if you use the Lyapunov function, which is basically energy function, you take the derivative, you found that actually energy is reserved. So that's why it's actually, is moving like that. Here is some typical sort of example you can see is that if you choose different k, for example, k is greater than 0, less than 1, and this is an ellipse type of stable motions, but it's actually this way, And if you do this, change it to this greater than 1, and you do this, right? And the issue is, can you stabilize the system? In theory, we know that you can't. You can't. The issue is that you only have one state, dimension is 2. There's one missing. You cannot have a global stabilization problem as a controller. But if you do the switching, you actually can. Why you can do that? It's very sort of intuitive. If you think that, if you look at this trajectory in this part, this trajectory is actually coming closer to the origin, right? And if you look at this part, this trajectory from here is coming closer to the path. So what you do is very simple switch, right? In here, I take this control. And in here, I take this control. So you can see like here, jump, 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 eventually stabilize. So any two systems, stable, unstable, you can always find a way to do the switching to make it asymptotic stable. So that's actually strength of switching control. So this appears to be sort of defy sort of the conventional wisdom. Say, hey, you don't have enough states. You can't stabilize system. But this is actually what I'm talking about later on. It's not actually real sort of a full state feedback. So that's exactly what it do. So, but the mathematics, as I said before, intuitively you can do it. And mathematics, they will be right. There will be some way you can describe it. So here is a way. You see another Lyapunov function. You take the derivative, and you can see that on each different phase in here, the energy is shrinking. So overall system is just stabilized. Yeah. So this turns out to be, looks like untrue, too good to be true. But this is also, it is not, as I said, single state feedback, because even so, you do have a feedback, single state feedback. But if you look at the conditions, it's actually velocity. So it's actually implicitly there's a derivative information. There's no explicit derivative information. So it does not defy the common sense of this, the stability. Okay. So this is, I call it switching control, because there's no sliding, right? So another one is, if I change the switching line to this, right, we know that if C is greater than 0, the whole motion is actually asymptotic or stable motion. You do the same thing. The principle is the same, right? You can do that. It's the same that you can see that there's going to be a swing, right? Swing, And if you do further, and you found, if you look closer, what you found is you found some interesting behavior here, around here, So if we go further, you can see this red stuff. So this is a very interesting part, is in the way that all trajectories from any other place after swing, it will sucked into it. That's actually the sliding mode, right? That's sliding mode. You can see anywhere starts the trajectory coming to here, and from bottom coming to here, it will stay there forever. So what that means you can have this kind of motion is mixed of swinging in control and also sliding mode. So, okay. So mathematically, you can certainly prove that this is a typical sliding mode control. Now you can see that that's the basic sliding mode, right? That's what we call sliding mode. Sliding means they not reach there, they never leave it. Okay. Now, so basically, is the old sliding mode, even say over last 50, 60 years now, the key hasn't changed. The fundamentals hasn't changed. We all know that. Most of you would know that. Firstly, you need to find the switch manifold, right? That represent what you wanted, and then you design the switching control. Switching control is most effective because that's usually the fastest way to make sure that trajectory coming into it and stay in it. And then you make sure that in the switch manifold and it's become attractor. Right? But they are actually if you look at, there are many papers actually using this, which is basically wrong, right? Because this is not necessarily guaranteed the sliding mode. It's only guaranteed that it's actually getting closer to the S equally. It doesn't mean that it will reach there in finite time. So if you use this control, you probably won't get a sliding mode at all because any trajectory coming from state goes straight into the origin, satisfy this condition, right? So you have to, in finite time, reach the manifold. Okay, so here is some of the geographic demonstration is. So you have a linear system. What you do is you design the switch manifold. You just make sure trajectory from here coming here and stay there, just never leave it. So here is basically we call the switching sliding sort of mode, right? But the issue is then how do you define the motion here, right? That's become an issue. So if you think about, let's say, how do I define the mode? Then you come back to your textbook in differential equations. What it says is the existence and uniqueness of solution of differential equation. For any differential equation to have the solution exists and unique is the function has to be smooth. But once you not be confused with switched control, there's another group of studies looking at switch control. So this is actually another kind of a switch control, similar to like a sliding mode. They do the switch control devices, but the issue is the sliding mode is prohibited. Right? It means they also need a switch manifold. The switch manifold can only be attracted from one side, and when they're passing it, they has to leave. Right? So that's another kind of a switching control. So this is another very hot topic pursued by the many people. But by assuming that you can see that then the system is easier to design. What happens is if from this time and taking this time reaching that switch manifold. And during this time, it is continuous, right? There's a smooth control. So you basically can use any controller design, any linear control can design it. And when they switch to other place, because it will take some time to reach, to go out and reach back. So in that time, you take another controller design. So you can switch this control. But then the issue is, well, if you, for each individual part of the system, you have a stabilizing controller, whether you connected them together, you have a global stabilization controller. And the answer is no, right? So people use the idea. So if I have a one Lyapunov function, which is energy, ensure that every control under this Lyapunov function or composite Lyapunov function, the energy is shrinking, guarantee consistent shrinking, then the system will stable, asymptotic stable. But the issue is it's very hard. You know that it's very hard to find such a solution. You have a few controllers. How can you find a few controllers satisfy one equation? Sometimes it's very hard. But this is just another very hot research. But there's another one which is unusual. You don't see many often. But this is another typical switching a type. We call that this is actually Zeno behaviors, right? We all have experience in our childhood. If you have a ball thrown on the ground and ball is bouncing, and we don't know how many times it bounced, but eventually settled. But if you think about it as a state, it's actually, it's a switching. Right? So it's actually bouncing infinite time to reach stability point in finite time. So this is a much more, it's rare, but it's a mechanical system. You do have this system. So this, in general, anything to do switching, you could have three. One is sliding mode, sometimes occurs. One is we call the switch mode. Okay, there's a switch mode, and one is a zero mode. Right, zero mode is rare, but usually it's those two things. So any of the non-motions is actually a mix of those things. Okay. Now the next question is, I want to basically just very quickly brief look at the challenges is still facing sliding mode control theory even after 60 years, more than 60 years. We know that chattering is a huge problem. That's why keep our research very busy, and it will continue to be busy for next maybe 10 or 20 years. It's partially because the switching, all switching effectiveness, ideal sliding mode require infinite switching. When I found the switching cross the line, I just immediately switch off. But the physical devices cannot do that. So there's always a little delay or parasite kind of dynamics. You got this kind of unideal chattering. So chattering is, that it's not very good for some mechanical systems. It's a system not very good. Have found a way. Matched and unmatched uncertainty is always a problem. We know that in theory you can always find a big enough controller mechanism overcome it, but associated with that will be severe chattering. Right? So what people will do is they try to estimate using whatever methodology to estimate it, and then you use much less crude control, switch control to control it, so reduce the chattering. So that's become another issue. Lots of research, that's neurophysiology, all these kind of things. And another one is unmodeled dynamics. This is also similar to the match and set, but you need to rather have some kind of model to simulate the unmodeled dynamics. And you know better, you use less force and reduce chattering. So that's basically the current issue. Another issue is here is I'm talking about generality versus particularity is basically sliding mode design is an art. Right? The theory is very simple. But when you solve a particular problem, you must find a specific physical behavior or features and design very effective way. So basically control theory, the moving the way is no longer very general theory. Anything very general has to be very conservative. It means you have to sort of overkill. So this stage we call the smart control is if you have a very smart device, you know better, you can basically take the advantage of system internal dynamics and use that as a control. Right? For example, in Tai Chi or Yoga is typical. For example, Tai Chi is typical example. Their teaching is you use your enemy force to defeat enemy. Rather you confronting. There's a boxing is confronting. I'm stronger than you are confronting. I think yoga would be similar thing. Is understand your body, using the flow and control it. So you use very little force. You can control very well. So that's become the trend. Another way is that integration. That's lots of work so far is integration with many other methods in sliding mode and with sort of intelligent system, with optimization, with all these different kind of things. So certainly there will be still a lot of work to be done in the future. Okay, so this is about sliding mode. So next thing I want to talk about, this is the focus of this talk, is discrete time sliding mode. So first thing I want to talk about is here is some of this is the general discrete time control system. We know that these days the control systems are implemented digitally. So even so, when you design it in continuous time, it's easy to design, but when you implement it, it is still in digital. You have to digitize it. So currently, if you classify the discrete time design, there's two types of thing. Right? One type of thing I call the discretization design. Actually, somebody else called it in the continuous time system. Is they call the discretization design means you use the controller designed in continuous time domain, which is much easier to do, and then you digitize it. Right? With from engineering point of view, is very intuitive, right? And then the issue is what kind of a problem we bring by using digitization. So that's one issue. And the second way you do is you call discrete time design, means that you convert all the design principle systems into discrete time. So you're dealing with discrete time model directly, and you design it, right? In digital control design. So there's another set of methodologies. In linear system, these two systems does not make much difference. You can say they are equivalent. But if you have a non-smooth system, non-linear system, if you have a non-smooth system like a switching discontinuous system, then there is a drastically different, two kind of a behaviors. But we will show you later on. So this is a typical way you discretize it. You have a linear the differential equations. Usually we deal with linear ones, so you're basically using zero order holder. You hold the control, and then you discretize it. You're basically dealing with this discretization. So one way you can do is this UK replaced by the continuous time controller and digitize it. You put it on to see how it goes, right? Another way is you basically using the principle. Here is some of the summary. Is another way using the continuous time principle convert in discrete time version, and using that principle to design the system. So here are some of the example you can see is that the earliest work in 1990. This is I think from Slovenia. I think the guy. Yeah, he firstly proposed the digital sliding model. What he says, he said, if this is sort of a necessary sufficient condition for sliding model to exist, what about if I replace this? Right? Looks quite intuitive, right? But it turned out to be only a necessary. Means that this one guaranteed the stability, this one does not. It's only guaranteed approaching the system. I'll show you an example. And then people further, a few other people, they're trying to say, hey, that's not necessary. So they basically make a much more you can see it's much more conservative. So they say, if this is the condition, the discrete time is I want to make sure at every moment the energy is shrinking, right? And I will show you that it's also very conservative as well. This one it just does not guarantee the stability, and this one is very conservative. So here is some of the chart you can see is that you can see this is actually the necessary condition, right? You can see that it's switching, right? It's every time switching, but it's the magnitude very bigger and bigger, eventually unstable, right? It's gone. So that's why it's only necessary. It's not sufficient. You have to have this kind of a motion. And this one is the sufficient condition. What that means? That means you basically every point, next point, future point, the energy will be smaller than the previous point. So you can see that this is a thing. You can see that from here to here. I think is which one is here's you can see that it's a distance between the energy. Because the energy is measured by the distance, right? It's closer, right? And you can see closer. Eventually, you press that. But normally, normal behavior is this, right? If you digitize, normal behavior is this. You can see that it's actually 2 times cross and jump up is because other side control too strong, and jump 2 points, come down and jump, and come down and jump, come down, and then sometimes they have 2 points. It looks like a very irregular. So this one does not satisfy because if you look at individual point, you can see the distance here is smaller than distance here, next point. But doesn't really matter. The whole system eventually will converge. So what that means those kind of criteria, even so it looks very good, but when you design it, it's very hard to design. That's why if you look at the literature, they put up very long, even for single input, they put up very long equations, very complicated, So that's, yeah. So another one is very sort of engineering approach is really by Professor Gao from China. He died, unfortunately. He basically, what the person did is he forced the control into some particular behavior. You basically usually just the bam, 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 bam behavior, right? He said, I want to control like that. And then you use that as a principle. You can prove that this eventually converges to a band and use that principle to design controller. And certainly in this another area is multi-rate. Multi-rate is Professor Bandipalia group has done a lot of work. It's very original in those aspects. Is you have 2 sampling rate. One is for control, and one is actually system state. It's much faster. So of course, when you have much faster, you have much more accurate system states, and then how do you design the control? So that certainly is another type of work. So this actually I call discrete time design. So another design I want to talk about, discretization design, which is the one I have done quite a bit of work, is to look at these discretization behaviors. So discretization design is basically, as I said, because continuous time domain design is very easy. So you design to take the calculate the controller and digitize it, put on the system, right? And the issue is then, if you digitize it, because sampling rate changing, so sampling rate become a variable, right? So how that kind of variable affects system performance? That's actually the key issue. You simply cannot just digitize it, put it on. There will be something interesting occurs. So the basically is simplicity, right? It's very easy to design. So you basically just use that design and instead of the one we talked about before. However, this advantage is that we just unconsciously introduce a sampling rate, which is another dimension of dynamics people don't usually take into account. Right? So what I'm demonstrating is if you look at that sampling rate as a variable changing from small to big, what kind of behavior you will see. So that's what we're trying to do. So again, let's look at a very simple example. This is another second order equations. You can see that if I take two controllers, one is this, one is the two control structures, right? And we know that's going to be global stable because it's not a real single feedback. It's actually single state. It's actually here is contained velocity, so it's not a problem, right? So you can do it. So what you can do basically, because you switch between these two controls, you basically have it's a piecing together two motions. You just depends on which area they are, you take the control actions. So eventually, this actually from physical phase plan is here is the dynamics you can understand is for the positive sign is that you have this kind of similar to the one we had before is ellipse type kind of behaviors, right? And for this, if I take another sign, another controller, because in this case this is negative, so what do you have? You will definitely have two eigenvalue. One is positive, one is negative. What that means? That means you have this kind of the behavior where you can see that in the state space there's one eigenvalue determining the asymptotic stable asymptote, and there's another asymptote which is unstable. So system, you know that will converge to the asymptotic stable asymptote and leave from another unstable asymptote. You see that? Unstable. But we don't worry about it because we do a switching. We only take the part we are interested. So if you look at this, you can see that if anything above if this is the switching law, anything above that, I'll take that. So trajectory will definitely get there, right? That's very important to get there in finite time. So, but when the trajectory coming across the switching line, you can't using a stable sort of controller do that, because stable controller, the motion will always move in that direction. Right? Of course, is it stable? It's a for example here. If it's stable, means that the x is positive, so x dot is negative. If of course it goes, it can't change. You reverse the action. You can't. The only way is the system has to be unstable. So here is the play. Is if I take this part, you can see unstable part. You bring the state back. So that's become sliding mode. So that's a principle. Very simple principle. You can see that. Okay, but if you digitize it, right, that could be a problem. The first problem you can see is that if you digitize it, take a little bit bigger step size. The sampling step size. You can see that it's actually this is like chattering, but it's still not bad. It's actually switching like still following the switching manifold, right? But if you just change a little bit more, but you can see like that, that's first in the beginning it's puzzled us. We just don't know what to do. So what's happening on this? Right. So it's certainly the discretization is if using the sampling will cause all different problems. Another thing is usually in engineering. I mean, this is I think h equal to 0.1 or something. Engineering, we know that okay, if I have this strange behavior, that's okay. I mean, I can choose small enough sampling rate to reduce the problem. And what I say here is that statement only applicable to continuous smooth control. it does not applicable to the discrete control, in particular of discontinuous control. Why I say that? This is a typical example, right? The same controller, the system, you can do the simulation, at home. You can take the parameter. What you found is you found that if h equals to 0.0158, and this is basically a very perfect sliding mode. But if you change it, only these digits, this is still very good. It's about, I think, 1 milliseconds. Usually, the usual sampling rate 10 milliseconds, It's still very good, but you can see that, for that, this is like that. If you increase a bit, I think if you increase 0.017, the system is unstable, right? So what that means is actually the stability is nothing to do with how small sampling rate is. So smallness is actually related to the boundary conditions. In this case, is all the system parameters form these kind of actually boundaries. And unfortunately, the h you choose is just so close to the boundaries. Boundary means if you're below that, stable. Above that, unstable. It's so close to it. So you just increase a bit, you're overshooting. Right? So this continuous system is really very, you have to pay lots of attention. It's nothing, it's some of the behaviors, you won't see it in continuous and smooth control. Okay. So here is another one. That one just tells you, there is a stability issue. Another one is, okay, if the system is stable, what kind of behaviors, right? So here is another interesting swing system, control system you can see, which is very close to time optimal. You can see that if you just switch between S like that and the bam, 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 we know there's a little sliding mode occurs. So what you do here is if you increase the sampling rate, right? You increase bit by bit. You can see that the system, here is the system H is 0.1. The system is not bad, but it's actually, there's, looks like a bit of overshooting. If you increase further, you can see that it's actually isolating and some stage it's become a limited circle. Right. So this is looks quite strange, but it's not it is still sort of if I show you more. If you start for one simple, you can say that for that one h is choose too big, then but if I choose h is fixed h, and I start from different initial conditions. And you can say the system is very complex. For some initial conditions, you have a behavior is period 2. Period 2 is very simple because you switch between two systems. So each system has a non-zero equilibrium point. So you switch between. So that's actually expected. But if you choose different parameter, initial condition, you got 4. How many of these? 6, 8, 10, 12. You actually get many periodic behaviors. So this is actually very the very interesting. Only exists in the switching system. So you got to be very careful with switching. You can see that some of the chart. You can see that actually, for the different type of switching patterns, period 2, period 4. And this is initial conditions. You can get as many as you like, right? And so far, we still don't understand how many they can get. We don't know what's the upper limit. That's very mathematically intense if you want to do the study. Okay, so basically, what I'm trying to show you is some of the interesting example and behavior. So basically, if you use a discretization method, the one thing you have to be careful is this sampling rate, a sampling period become a variable, right? And the second issue, when you talk stability and stabilization, you must accept you cannot converge to zero in finite time or in infinite time. You simply cannot do that. So what you have to worry about is stability. Means how big the region is. Eventually, all system will converge to it. There's no way you can converge to zero. Absolutely no way. Right? So you have to, to the second. So that's you should do. So it's a stability problem. And also the other issue is though if a sampling rate is a variables, how that actually variable affects the robustness? If sampling rate is for example, if a sampling period is close to zero, we know that that's close to close to infinite switchings. So it's very near the ideal robustness. But sampling is a little bigger, you get a worse, right? And how do you measure that? So that's become performance indicator, measure it. And you understand that the thing is we need to understand behavior. Then the thing is when you understand better, you can design the controller in a particular way to overcome the problem. Accept that's a problem and do it. Okay, I'll just show you some of the results before we talk about the other broader issues. Here is some of the work we've done for single input. You can see it's very familiar single input controller system. You can design the switch manifold, choose a Lipschitz polynomial so it's asymptotic stable. You do this equivalent control, your switching control, and you can mathematically prove that it actually converges to the switch manifold in finite time. It's very important. If it's not in finite time, it's not sliding mode, right? You never have a sliding, so let's make sure that. And if you digitize it, then what you want to see is, as we already saw some different periodic behaviors, what you want to see is, firstly, you have to look at how the sort of trajectory performs. So this is some of the theory we used. Somebody called using the symbolic dynamics. So what symbolic dynamics does is they actually build a correspondence between the symbols and the actual system trajectories, one-to-one response. So if you understand how the symbol sequence behaviors, you understand the system. The reason of doing that is the benefit of doing that. For example, if you look at you cut this space into quite a few areas, and then you just look at trajectory passing this area, then you just record which area it passed, instead of looking at actual trajectory where it goes to. Right? So it's much simpler. So that's very important. And all switching sliding mode control is typical because with switching, if you consider that as symbol, you basically had a -1 sequence. Sometimes you have a -1, +1, -1, -1, +1. You have all the combinations. So, and this is just some of the example is to show you the equivalence between the mapping. For example, you have 0, 1, and every time you have this kind of fractional part of 2x. So every time you split into half, one half to the 0, 1, another half to 0, 1, again. So you just basically record which part they are in. So it turned out to be that one is equivalent to the number you're dealing with. I don't think I want to sort of do it again. So it's a very simple operation. So basically using that, you can sort of analyze the system, you digitize the whole system, and this is the condition we got. So it's in early 2000. So the condition is that if you really want to, the equivalent control, if you really want to make sure the system is stable in the Lyapunov, I'm not saying asymptotic stable. I say it's stable, right? So it actually converges somewhere, and they just stay in it. It doesn't come out, right? Firstly, you have this matrix, and this is actually equations we got is very useful. Is usually people the result from researchers, the approximation, they said, hey, eventually the steady state is converge to an area which is OH, right? But OH doesn't mean anything because OH could be 1,000 multiplied by H. You don't know how big. There's a limited. So what we are able to do is eventually we have a sort of analytical solution here, and you can basically using it for engineering design. So how do you do that? Is that, for example, if you know that I want the system precision is 10 to the -4, so you can put a 10 to the -4 here, and because those equations are function of sampling period, and then you just solve it, eventually you will find up limit. So if you tell me you want precision 10 to the -4, I will tell you that the maximum sampling period is 10 to the -3 or 2.10 to the -7. I can tell you exactly how to deliver that precision. So this is a very mathematical, but it just to give you a very good indication of how you should design the sampling rate. Okay. And also there's similar very complex behavior. So far we only can explore some of the properties, but you can see that for the second order system, you can see there's a period 2, there's a period 4. This is the boundary, and also there is I'll show you another one. See, there's a 2, 4, and also this is a very strange one. I don't think you have seen before. Is it doesn't converge to it at all. If you particular sampling rate, they actually just following the boundaries. So discretization can bring all sort of Very interesting behavior. Well, the next question is how do you do with sort of multi-input system? We did the work, published in a transaction AC. Similar result, you can understand, you build some kind of conditions, stability conditions and boundaries. And you build this relationship between all the symbols. You can read the paper later on. And this is just some of the behaviors, similar behaviors. So what it says is you have, for example, for this example, you have two controls, you have two channels, and then there's two symbolic sequences. Then you want to look at the relation between symbolic sequences and what kind of behavior it has. So this is actually some of the behavior we have. You can see there's a 4, there's 6, there's 8. There's many other, very strange behavior. And you can also calculate this kind of table, right? So certainly that helps you to understand how discretization impact on the sliding mode. Okay, so I think the next one I really want to talk about is summarize the issues. I think we probably spend a bit more time and look at that. So as I said before, sliding mode has two directions. One is discrete time design. One is discretization design. So in discrete time design, even so there are many research work, broadly, as I said before, if you really follow the pure discretization design principles, using those criteria, it's very difficult to work out actually the solution. It's very complex, very difficult. So the how to do it still is kind of open questions. It's very complex. And the second issue is that really sliding mode? When you digitize it, you have to say that it's switching. It's similar to switching system as well. So that's become how do you define it? There are many definitions. Chattering is, of course, is a problem, and this looks like many people follow this direction in research. Is they force this discrete time sliding mode into particular patterns, and then drive the design controller to reach it. It looks like very practical. The second issue is here is some of the findings. Firstly, is we realize there exist chaotic behaviors, right? Chaos. What does chaos say? Chaos basically say that if you have same system, you start from two initial conditions very close to each other. If you run the infinite time, these two trajectories end up to almost just so far apart, right? If you look at as I mentioned before, ordinary differential equation, the existence and uniqueness, we say that it's actually, if you have this equation satisfy Lipschitz conditions, the uniqueness of solutions trajectory is guaranteed. But it never tells you if two trajectories start from very close, they're all unique where they are. So chaos is actually study this kind of sensitivity to initial conditions. That's chaos, right? It's interesting that we found in this. But actually any switching system will have this behavior, right? And another issue is a nonlinear system. Even in this simple system that we use a linear system, because we can exactly digitize it, so we don't lose actually dynamic system apart from at the switching moments. But if you think about nonlinear system, you have to use like approximation, Euler, Runge-Kutta, and some other approximations, And the issue is if you design controller, digitize it, and that's actually your approximate model, whether this digitized controller can actually control it, because that's actually approximate model. Even so it can control it, doesn't mean they control the original system. So there must be a condition. So that's become very interesting research questions. And the last point I want to mention is that this is not simply sliding mode. In time optimal, in actually digital filters with nonlinearity, they have similar problem. Much richer behaviors. In digital, we know that digital filter usually is linear, right? It means that fixing low pass filter, you have an ideal situation. Any signal coming to here will be passing low frequency passing and high frequency filter out. But if you implement in circuitries, in every physical element parts have a limit. So basically, you have actually up and a lower limit. You can't higher than that. So basically, if you think about that in real implementation, the filter would be switching between three systems. One is the linear system, ideal one. Another one is the limitations, physical limitations, saturated. So it's switching, right? So there's the the behavior is similar, very rich, even very colorful as well, beautiful, fractals. I don't want to demonstrate today, but that's something you need to draw attention. Another part of work is really some of it's much broader than just the discretization. That's just some of I thought about it. I thought this is a very strong sliding mode group. I have to say something meaningful, right? Not just too superficial. The issue is certainly is we talk. There's a lot of work done these days in finite time sliding mode control. So finite time sliding mode control means that we know that you have to reach the sliding manifold in finite time. But if you think about this linear manifolds, linear manifold means it has actually eigenvalues. What that means any state in the linear manifold will converge to zero in infinite time. It never get there. It's just closer, but it never get there, which is not good for precision control. Well, you might say, hey, I don't care. I just increase the gain, the system control gain. But if you look to make it faster, but if you do that, you have to make your actually controller much stronger, energy, not energy efficient, which is not desirable. But you still have the similar problem. It's just it's proportional to the distance to the equivalent point. It's so close, doesn't matter how big a gain, you're still slow. You never get there. So that's why I came to people early on, people have some initial ideas, so we extend it. We establish a set of theory. Basically, the sliding manifold itself is finite time, which has been picked up by some mechanical people who look at precision control. Basically, what that does is that if you have this kind of a switching, so a terminus slide, I forgot to write it here, is so terminus sliding mode is, for example, the linear one is x dot plus s equal to 0. So what we did is x dot plus x to the power of 1 over 3 is a fraction. You choose that. The benefit of choosing that, if you do the calculation, you do the equivalent eigenvalue, you found that actually the gain is inverse proportional to the distance to the equivalent point. So closer to the point, the gain itself increase. So basically, if you have this much energy, you just first use it. One is close to it, the energy is smaller, so you can increase the energy still within the bound. So system actually converge much faster. So that's why I've been sort of attractive for that. And also there's another one, second order sliding. But second order sliding is basically swing control. I don't consider it as sliding mode. It's actually swing control. So, but the problem is if you digitize this kind of a non-smooth one, you got more problem. More problem is that what we demonstrate, which we publish in Automatica, is when you have this non-smooth element, you digitize it, you actually create these small regions. Inside these little regions, system is actually unstable, and outside the region, all the trajectory come into here. The reason we found out is we did some simulation, and we just realized that they never converge to 0. We thought we choose smaller h. It never do it. So eventually we did some mathematical analysis. We realized that actually there's a two semi-stable point, up limit, bound limit. On this side come here, this come here. Inside is coming to converge to these two boundaries. But of course you can tune the parameter so that that boundary is smaller. Then that's determined how that determined is by the precision, but you can do it. But there's certain. But the thing we did is only very simple first order differential equation. When you do the second order, it's very hard. Discrete time even harder. So that's why the reason is there's not much good work beyond second order. Very hard. But I think it will bring some very good benefits. The thing from the application we actually use in real time in the application in the machine for a factory, for grinding machine companies, it demonstrated perform extremely well. It's actually robust. Actually, this terminal sliding mode is actually much higher. It's kind of equivalent to a much higher high gain controller. So that's why they actually converge fast. It's high gain. It's actually converge very fast and robust. High gain is robust because the gain is very high. Equivalent very high. So that's some benefit of using that. And another work is a lot of work on that. Even though we wrote, the paper. I think it looks like people continue to use that. The last thing I want to mention, this is actually what I see is a frontier of sliding mode. Where it goes. Why I say that is in the future, in particular in the industrial control system, in the future, it's no longer you have local controllers. You have it's actually network control environment. You have a workstation is actually sending control to the individual controllers. Transmissions through either wireless, wired, and then that then you got a problem. Firstly, this transmission have time delay, but that's not too bad. Time delay is like a discretization. Even so, this time delay sometimes vary, but you can expect this chattering. But another thing which is the most important is we're not dealing with in usual controls design is sort of a packet dropout. Packet dropout is if you look at the automobile, what the telecommunication company does is they first collect all the sort of voices in that period of time into a packet, and then they send the packet out, and then they decompose it, they do it. And sometimes we know that you say, that suddenly it broke. It's drop out, right? It randomly drop out. For communication, it's not an issue. We just say, dial again. For control, it is an issue. Firstly, when you drop out, what are you going to do? The control is going to be controlled. Secondly, is if it's delayed, it's drop out, that control signal is no longer useful because it's delayed or being sort of compromised. So you can't use that. So you see, that's become a very serious issue in the future. So certainly that scenarios would, those are things would bring a new theory. So it certainly is much complex because this time delay and the packet dropout. This is there's a statistical patterns, and time delays sometimes is a time varying as well. So it looks like you have a time varying time delay, and like a time discretization. Like that, a time delay discretization. So certainly how to look at that as well. We actually did some further work to look at which sort of existing methods is more robust than the traditional method. And it turned out to be that those boundary layers, those approximations produce better results than the traditional one, because they remove the switching, So they basically force the system into a domain, and then the system in that domain coming here. So when you have time delay, it has much less impact on the performances. So that's actually very interesting observation. So now we're actually trying to do some mathematical analysis to demonstrate, yes, you can do that. Certainly this is going to bring many new sort of methods for design and application. Another thing I think I forgot to bring here is like the talk I gave yesterday is in smart grid. The smart grid, that the smart system, power system is basically, there are many switches, right? So power system is typical area for sliding mode because the switching is inherent. Usually you have designed the power electronics devices, you only have a few values to choose from. Every time you look at the condition, you choose this, choose this, choose this, choose this, And the issue is if you have many of those switches around, they all switching to start switching, what kind of emerging behavior, So that's certainly will bring a new sort of frontier to the sliding mode control. So I think that's it's the future for you guys to, if anybody interested, you can continue the research. I think I should probably just stop here. It's close 4:00. Thank you very much, and hopefully my talk is make some sense. Thank you very much.
I open the talk now for some few minutes.
Yeah.
We can some questions and answer session. So I will just open to the audience. If there are any questions, few questions we can take. We have some time. Then you're most welcome to ask.
Yes.
In case of terminal sliding mode, how would the closed pole locations? Like, are they going to infinite immediately, and then we are getting finite time?
Well, it's no longer finite time because, as I mentioned before, when you have a switch, when you digitize it, you basically no longer have an equilibrium point as zero as equilibrium point, right? Because in any moment when you switch on this value or that value, that's a constant. For that equation, you have a non-zero equilibrium point. So you basically switch between two equilibrium points, So So the only thing you have is it will converge very fast to these two equilibrium points, very fast. And then they just converge to either here or either here. It doesn't converge to zero. It's still final time fast response, but you don't converge to equilibrium point if you digitize it. Yeah.
But is it like the closed loop poles of terminal sliding mode will be harder as compared to the closed loop poles of the normal sliding mode control?
Sorry, can you repeat again?
See, in case of normal sliding mode control, which is not terminal sliding mode control,
Yeah.
in that we find out the closed loop poles of the system during sliding.
Yeah.
So they are located somewhere, and then we say that this is asymptotically stable system.
Yeah.
Poles are located on the left half of the
Yeah.
S-plane.
Yeah.
In case of terminal sliding mode, where these poles will be located, that I am trying to understand.
Well, I think if you look at the conventional control, right, linear control, when you digitize it, it will not converge to zero. They only converge to the place where it is proportional to the sampling rate, right? They never converge to zero. It doesn't.
I think that her question is that in terminal sliding mode, where the poles are there, but if I understand correctly, in terminal sliding mode, it's a nonlinear system.
Yeah.
So no question of
There's a pole. I mean, that's what I'm trying to say. There's an equivalent. You can do looks like linear system. There's an equivalent pole. That pole is inverse proportional to the distance. It's nonlinear pole. But you can build this. That pole is actually, when you closer, that gain is increased. So you can build that relationship, yeah. But it just converged somewhere, it just stopped. While without that one, it will converge to a place where it's actually just proportional to the period, to the sampling period, It still doesn't converge to zero exactly, Yeah.
So, more one or two questions? Any questions?
No question? Okay.
Okay, then we thank Professor Zeng for giving this nice and illuminating talk on discrete time sliding mode control. And I hope you enjoyed the lecture. And of course, these days the email is there, his papers are there, all of you can interact, and again you can gain more knowledge on this subject. So once again, please join in thanking Professor.
Okay. All right. Thank you very much.